Now it's time for the next talk about Tor. These people are not designing Tor, they are using Tor for their application, which allows you to create a virtual network over a Tor connection. So, well, Yvonne, well, just I hand the mic to them and talk.
Okay, welcome everybody to our talk about onioncat. First, before we start, we just introduce ourselves. That's me. My name is Bernhard Fischer. I'm a lecturer at the University of St. Pölten in Austria. And my colleague is Daniel Haslinger. He's a student there, and we are both in the area of IT security, operating systems, and programming and stuff like that. And we are both have been in the ISP area for several years. So we are now going to talk about onioncat. Just a few words before. onioncat started at the 23rd Congress here 2 years ago. We both like Tor very much, and we have been interested in this project and watching it for years before, and we had a talk together and in a bar with a beer, and we said it would be really nice if we could contribute to the Tor project. So we're really proud that we can present this today. Okay, first let's have a look at what we are going to talk about. First, we'd like to introduce the hidden services a little bit in detail for you. I don't know if anybody is familiar with this. We won't talk about Tor itself because I assume everybody in here knows what Tor is, and especially the speaker before, Roger, gave you an overview about Tor, and I think there is no man in the world who could explain more about Tor than Roger. Okay, next we dig into details of onioncat. We'll show you how it works, what the basic ideas is, and give you an architectural overview of the internals. Well, yes, then next we have the applications to give you an idea about what onioncat can be used for and what we would like that onioncat will be used for. And, well, last but not least, bootstrapping onioncat. onioncat is a really small project currently. It's just us two. And I talked with lots of people here in the Congress, but it's still a really small user group, so we hope that we have some ideas to give you to use onioncat in a way that the community grows. Okay, so let's have a look at hidden services.
Yeah, a hidden service is a location hidden service inside the Tor network. You can only access it through the Tor network. A few months ago, we installed such a service in a garage somewhere. It is also physically hidden. And the hidden services within the Tor network can be accessed without knowing where they are. So when client and server want to communicate, they don't have to know either the location of the server or of the client. The connections typically stay within Tor, and they do not need the Tor typical exit nodes, which is a very vital thing for the hidden services and the security within. So how do the client and the server find each other? To stay simple, the server and the client connect through their very own Tor circuit to a rendezvous node which exchange the data between it. In fact, this is a little bit more complicated, but this describes the technology quite well. So the server first raises a connection to a so-called rendezvous node. The client does this also. You see the typical circuit that every Tor client or every Tor application uses. And then the rendezvous node just sticks the two together and exchanges the data between them. Tor is quite slow, so it takes a while.
The presentation is given across Tor. No, not really.
So, how are hidden services used? If you need to access a hidden service, you need a running Tor installation and a software that uses the Tor SOCKS interface, either through libraries that are aware from SOCKS, or maybe a software that uses the Tor SOCKS Ethernet interface directly. If an onion address has been detected, Tor will simply intercept the request and will route the connection into the Tor network to the hidden service as shown before. Oh, just a moment. It was too quick. Owned by technology. So, here we are. Damn it. Okay. Look at me. As soon as you enter the onion key or the onion address inside an application that uses Tor or the SOCKS interface within Tor, you just enter the onion key to a web browser, for example into Iceweasel or so on, and the interception will be done by Tor, and you will be routed to the service. So I hope it works now. Yeah. So the benefits of hidden locations, or location hidden services, is that you do not need exit nodes anymore. This is good because exit nodes are a very problematic thing. In fact, a very small amount of people want to be an exit node. That's depending on the country they may live in. And these connections the exit nodes make into the real internet are unencrypted. So hidden services provide some kind of end-to-end encryption, which would be not true if you use exit nodes for your connections. So what's wrong with those hidden services? They also have a catch. The onion rules are hard to remember. This is a fact which we try to resolve. We talk about it later. The SOCKS interface is not always easy to use. You have to, for example, you have to configure your applications to use SOCKS. This might require some knowledge on this topic. Also, the SOCKS does only transport TCP/IP. And last but not least, an issue we couldn't resolve in our project is that hidden services are damn slow. So what's our goal on these hidden services? We provide an easy and transparent way to use hidden services. Hidden services improve an individual's privacy enormous. So our intention is to make it usable for a broad amount of users out there. And so maybe get Tor and the hidden services a little boost. Our first solution to this problem, I mentioned it on the onion keys, which are hard to remember, was to implement the TCP-based name service. As soon as a hidden service rule is used, the Tor uses public and private key authentication to route it to the hidden services and to authenticate it. So due to this behavior, phishing is not possible anymore. Yeah, let's take a look. The next thing is we do not violate hidden services with our solution, which could be a problem if you use some kind of DNS in there without any interception before. There is also a really well-known service out there for name resolution. It's the DNS system. And so reinventing the wheel wasn't an option for us.
Okay, now let's dig into details what onioncat really does. So first, some basics. We'd like to provide an IP transparent interface. What SOCKS definitely not is. It's a TCP interface, so we'd like to have an IP transparent interface. And obviously there is the TANTAP driver available on more or less all operating systems. Also on Windows, of course. The OpenVPN guys did a good job there. Yes, okay, TANTAP devices are virtual interfaces, virtual network interfaces. They stay on your host. So it's like an Ethernet, but it's just virtual. You can put there an IP address, you can ping the IP address, you can, well, do everything what you can do with a normal Ethernet interface also. So, well, yes, that's one part. We configure this TON device or TON tap device, and so we have to the operating system side a native layer 2 or layer 3 interface. So all packets arriving to the kernel from wherever they could arrive, of course from other Ethernets or other TON top drivers or wherever, are routed by the kernel based on the kernel's routing table. And if there is an entry to the top device, it will route the packets to the top device. On the other end of the top device, there is then onioncat. So, well, you have the TON device, the top device, whatever, and you configure an IP address, and so you can send packets there. To give you a basic idea, I show you a picture with SOCAT. I think most of you know SOCAT. Maybe if you don't know SOCAT, you know NetCat. How many people know NetCat? Okay, not everybody, but okay. So to give a quick introduction to SOCAT. SOCAT is nothing else than a packet forwarder between file descriptors. And in Unix, every I/O channel you can think of like files, like TCP sockets, like well UDP, like pipes, whatever you imagine, are based on file descriptors. So you can forward data between them in the user land. Okay, and what SOCAT does, it opens an I/O channel on one hand and another I/O channel on the other end, and then just forwards data between them. So there could be on one end a file, on the other end a pipe, or on one end a file, on the other end a network device or a TON top device. And that's where our idea came from. We took SOCAT and configured it that it has on one end the TON top driver. So there is an interface I can assign an IP address to. Luckily, SOCAT, what NetCat not does is it provides a SOX4A interface on the other end. So I can configure SOCAT in a way that there is on one end of SOCAT a TON top device and on the other end a SOX4A device, well, socket. And of course, I use this SOX4A device to connect to the Tor proxy because the Tor proxy's interface is SOX. Okay, on the other end, this gray-shaped figure here is the Tor network. So on the other end is also a Tor node where we configure the hidden service. So the hidden service accepts TCP sockets. So we have to configure the SOCAT in that way that it accepts on one end TCP sockets, TCP connections, and it opens again a TON top device on the other end. So what we can do with this setup now is assign an IP address with ifconfig here, assign an IP address with ifconfig here, and we can start to ping to, well, do everything you can do with IP. Okay? That's the basic idea. But SOCAT does nothing dynamically. That's a manual setup. You have to set up everything manually. Install this, configure IP address here and here and here and so on. Yeah? Okay, it's just to give you an idea. So let's look at the next slide. Our idea was we want to provide a piece of software that does everything automatically. In a way that if you plug it in, you automatically get part of the community. That's not possible with this SOCAT way. So what we needed is some kind of migration from those .onion URLs to some other kind of addressing method. And of course, we are working with TON devices, so the addressing method of choice is IP. Okay? So we use especially IPv6. You will see later why this is the case. Well, why do we want to use IP addresses? Well, you know, every service in the world is based on IP. So if we use IP, we can also provide every service to work with onioncat. And some slides before we said, okay, .onion URLs are really hard to recognize. So if we have IP, there is a way to to make IP addresses more rememberable, that's DNS. Okay, so there is another part, Daniel already mentioned, the onion URLs provide some kind of authentication. They are strong related to a specific hidden service, and that's what we don't want to lose because it's a feature. So if you have an onion URL and you connect to this service, you can be sure, because the Tor network guarantees that you're really connected to this specific onion, to this specific hidden service, and not somewhere else. That's what he said about phishing. It's not possible. Okay, let's see how we did this migration.
Okay, let's look behind the scenes of the migration now. We first have the onion key we mentioned. An onion key is a base 32 encoded hash of the hidden service public key. So we have the hidden service private key, and the public key is generated out of the private key, so it's the key pair, in fact. We calculate an SHA-1 hash out of the public key, or Tor does it, and now we have an 160-bit hash of it. 80 bits of this 160-bit we convert through base 32, and we get an onion address. This is how the onion addresses are created. So how do we come to the IPv6 addresses here? This is the IPv6 local address format. We have the prefix, we have the global ID subnet, and the interface ID. And we want to get the onioncat addressing scheme. No. We just use the prefix, the global ID, and we have 48 bits for our new prefix for the onioncat addressing. And the rest, the 16-bit subnet and the 64-bit interface ID, are the 80 bits of the hidden service key. We can use now the hidden service key and put it into the 80 bits we get out of the subnet and the interface ID. So we just stripped out the subnet thing and pack everything inside it. So this is our new onioncat locator, and this is the IP address we get out of this migration. And the best thing on it, it is definitely worldwide unique, and this provides the ability for automatic configuration as soon as you start onioncat.
Okay, this IP address migration is the most important thing of all that stuff. On this is everything else based. The rest is just coding a piece of software which does the migration and okay. So let's have a look what the coding stuff does. What does onioncat internally? It opens a TON-top device. It then reads from the back end of the TON-top device through the kernel the IP packets which are coming in there through the routing table. Okay, then I read the IP header, I extract the destination IP address, then I can easily translate it to the .onion URL because the least significant 80 bits are in fact reflecting the onion ID directly. With this information I can connect to Tor, to the SOCKS interface, and request a hidden service connection. Tor does this itself, and when it returns and says, okay, connection is open, let's forward packets. Okay, that's the last point here. I'm just forwarding packets to this connection, which has of course this IP address as destination address. Okay, that looks like the figure before, just with a little difference. There we have now 3 Tor proxies and 3 onion-cats. It's not limited to 3, of course, it can be 2 to the power of 80, of course, in theory, yeah, okay. So we have not anymore this SOCAT part here, we have onioncat. That's SOCAT is the father of the name of onioncat, of course. So that's onioncat. Onioncat creates the TON-top device. It assigns the IP address itself. The IP address is determined from the local hidden service, which is configured here. And all the same stuff happens on the other onioncats. So each onioncat here is associated with a specific hidden service here, with a specific IP address for this hidden service. So if a packet comes in here, onioncat does the translation stuff, connects through the hidden service here, and packets are forwarded to this. And the rest does the kernel for us. We don't have to do anymore. The kernel receives packets and does with the packets as it does usual. Okay, let's look a bit into details of onioncat. It's a multi-threaded application. The most important thing is there is a peer list. We keep track in this peer list of which hidden services are currently connected, which IP addresses are assigned to them, which onion URLs and all that stuff. Then there are two main threads which are doing the data exchange, one on the receiving side and one on the sending side. Then there are two threads for accepting and accepting incoming and initiating outgoing connections. And last but not least, there are some supporting threads around. Okay. So the next picture shows you what onioncat internally looks like. There on the one end we have the local operating system, Linux or whatever. On the other end there is the Tor network. That means that's a Tor proxy, the local Tor proxy with the SOCKS interface. Okay? So and in between there sits onioncat, and if we assume that connections are already established, as shown in the previous picture with the 3 onion-cats. Packets arrive here from the local operating system. That's the tunnel receiver thread. It extracts the destination IP address, looks it up in the peer list, and forwards it to the Tor network. In the other end, there happens more or less the same thing, but we don't have to look up anything in the peer list. If packets receive from the Tor network, we just forward it to the TAN device, and then it gets to the kernel. That's all. Okay, let's see what happens if the connections are not established. There are two main threads involved in this. That's the SOCKS connector and the SOCKS socket acceptor. The SOCKS connector gets active if an IP address arrives on the tunnel end, which no peer is found in the peer list, which means there is no service, no connection to a hidden service already available. Then the tunnel receiver triggers this SOCKS connector. The SOCKS connector sends a SOCKS request to the Tor network connects, okay, and when the connect is okay, and when the connect is okay, we enter this to the peer list, this new peer, and packet forwarding can start. In the other end, there happens more or less the same thing. There is a socket acceptor. It's listening on the hidden services virtual, no, not on the virtual, on the real port here, of course. And if connections from someone else comes in here, Tor forwards it to the listening port here. The socket acceptor accepts this and enters the IP address in the peer list. There is a little problem here, because we do not know the IP address of the other end, of course, because packets, the Tor network is based on TCP, so we just see more or less, we don't have IP information, so I have to receive one first initial packet that the socket acceptor can extract the originating address, the source address of an IP packet. So this entrance here in the peer list can done not before a single packet arrives there, but okay. Okay, that's more or less all that happens in onioncat. So let's have a look at applications. What can we now do with this? Well, basically there are two applications we can think about. One is the traditional VPN use. We can just use it as a VPN across Tor. It's like OpenVPN. I think most of you know OpenVPN. It's a VPN like VPNs work. You can do the same thing with onioncat, with the difference that you do not use the internet, and traditional UDP, you use Tor as a transport for your data. And there's a nice feature in Tor, at least in the newer releases, or it's not releases, it's well before release, but you can download them. There is some kind of authorization built in hidden services, so you can supply your VPN users with a username and a password, more or less, that only connections happen to people knowing this password, okay? application we thinking about, or we thought about when creating onioncat, is that we want to build a global anonymous internet. If you don't have this authorization stuff, everybody can connect to everyone else with onioncat through Tor. And because of the hidden service, they can't locate each other. They can exchange data, but they don't know where they are and who they are. So that's the major thing, the major application of what we think what onioncat makes it useful. Okay. So if there is no authorization, you connect onioncat as it is here, as it is currently configured. You got this unique IP address, and through this migration scheme we presented before, every onioncat user, every onioncat user can connect to every other onioncat user. And then what can you do with this? You can transport any kind of data you like. It can be UDP, it can IP, TCP, whatever. Okay. There are some examples. You can mail, web chat, IRC, be creative. Whatever you can do with IP. Okay.
One of the applications we also intended is that you can use regular DNS to memorize the IP addresses you have, because you couldn't, as we said before, you wouldn't be able to use a regular DNS for the onion keys. Yeah, the modes of operation. We got two modes of operation. The first mode of operation is the tune mode. It's based on layer 3. And the second is the tab mode, based on layer 2. The TUN mode is easier to use and intended for providing one or more services, but just on one machine. So there's no routing capability. You just have services on your machine, and onioncat connects the services into the Tor network and into the hidden services. The tab mode is used for the total encapsulation of virtual machines. So if you plan to use, for example, VMware or another virtualization tool, you can provide virtual machines in there, and you can host services in there, and through the tab mode, the connection is routed into these machines. These operation modes are intransparent to the opposite onioncats, so they don't know if the other end uses the tab or the tune mode. So this is just easy to use in this way.
Well, yes, that's an important point. I think if you have a TUN onioncat on one end, you can have a tab onioncat on the other end. They do not. That's what means intransparent. The other onioncat does not see the layer 2 information, so it's completely layer 3 transparent, but not layer 2. And that was a little bit tricky in implementation, because the tab device actually is a layer 2 device, so I had to intercept the neighbor discovery protocol of the IPv6 to acknowledge the neighbor discoveries from the kernel. So that's the only part which is not transparent. Otherwise, it wouldn't work. Okay. The question was if you can set up the TUN mode with NUT on it. I'm not sure. As far as I know, there is no NUT defined for IPv6. But if you use IPv4, I'm not sure. I don't know if there is NUT available for IPv6. But of course, you can configure tunneling, IPv4 tunneling, IPv4 through IPv6. This will, of course, forward through onioncat, and on the IPv4 device, then you can apply NUT, of course. Okay, that's a simple application example about the tab device configuration. There, what you see here, the brown shaded figure is the host operating system, Linux or whatever. On this host operating system, you run the Tor and the onioncat in tab mode, which means it provides a virtual tab device with all routing features tab devices have. And then what you next have here is, it's just an example, you run two virtual machines with VMware, VirtualBox, whatever. And all these virtualization techniques also provide usually some kind of network interface. And what you next do is you configure a virtual bridge here with, for example, the bridge tools. I tested it with Linux, it works perfect. And you connect these devices together. So what you do then is connect these devices together, so each of them will see each other on layer 2. And then you configure your IPv6 onion IP address within the virtual machine. Of course, not on the top device, but within the virtual machine. So, and the nice behavior of this is that these machines are really completely encapsulated into the Tor or into the onioncat network. Because that's a little bit a problem which could occur, that you leak some information. That's not because of onioncat. That's always, if you provide hidden services, if you not configure that these services you provide in the right way, there may be information leaks. Okay, but if you have a completely encapsulated machine, there is no way to leak information. Of course, if you do not enter your username and who you are here, yeah? But not from outside, from the kernel, IP, whatever tables, okay? So, well, yes, this works really good. Let's talk about bootstrapping OnionCat. How do we put some life into the OnionCat scene?
Which is the reason why we are here now. What is available now? We got the fully functional onioncat client to download. It runs on Linux, on OpenBSD, FreeBSD, and on Mac OS X. We couldn't manage to port it to Windows right now because it's a little tricky thing to use the OpenVPN implementation. The OpenVPN guys did a very good job there. And you can get it on the URL we posted here. You don't have to remember it. You just go onto the slides we provide for downloading, or maybe you got the proceedings.
Yes, if you go to the homepage from the conference, there is, for each talk is a website. So if you go to our talks website, this URL you find there, so you don't have to write it down.
Okay. And we implemented the very first service for public use. It's the onioncat service registration website. You even don't have to remember the IPv6 address. And as soon as you're there, you can post your own services so that everyone that uses onioncat has the ability to browse through. There's no search engine, so this is a very easy way in wiki style to get the locations where you can get further information or services within onioncat. A service we already raised is an SMTP and MP3 service. We will provide an interface to register your very own mailbox there. It's not implemented right now, but you can just send us a mail to the mailing lists, and we will try to give you access to the whole system. We implemented DNS. This is a very tricky thing. We just invented a new top-level domain called .cat. And the DNS resolves the .cat addresses, but you can't just easily use it by inserting the IPv6 address into your named into your resolve.conf. So there is a little work to be done. Maybe anyone out there who is very familiar with DNS could help us there. That's bad.
Okay, somebody mentioned that this top-level domain already is in use for some country. I don't know. We also didn't know. Maybe we change it.
Is it a country or is it a free registration? Okay. Well,
Catalonian.
so much for geographics.
Okay, we are sorry for that.
But it would be a nice name, yeah? Okay. And we already have an IRC service. Some guy in the USA implemented an IRC server for us. And you can join us there. The channel is #onioncat. And yeah, let's talk about different things there. I hope we can populate the channel a little bit. Well, the only thing is maybe you have to wait a little bit for answers because we write very accurate, but Tor. Okay, what can you do now? The first thing is support the Tor project. Of course, the most important thing is the more users Tor has and the more users Tor can also use to provide the circuits, we think the speed will grow as soon as a huge amount of people use it. Also use onioncat and provide onioncat services. This is very important for the bootstrapping, of course, because the more services are available, the more interesting the whole thing will get for other people. And talk to us. We need feedback. We got a mailing list, onioncat@cypherpunk.at. We also will provide a mailing list inside onioncat through our onioncat mail server. And please help us porting onioncat to other OSs, especially Windows, because as we already mentioned, the thing is the OpenVPN trick inside there.
Porting it to Windows is, I think, important. We ported it ourselves to other operating systems, but as long as you stay in the Unix world, it's more or less easy. There is, well, some slight differences, but it's not a big deal to do this. But porting it to Windows is something different. There is nothing like /dev, so you can't connect to a character device or anything else. Well, we hope that maybe here is somebody who could help us a little bit in porting it there. I think that we should use the top driver from OpenVPN. I also talked to some guys from OpenVPN and I get some help from there, but it's not easy because I don't have any idea how to write software on Windows. Okay. Well, okay, so that's the major part. Are there any questions?
Could you maybe bridge that tab device you talked about? Could you maybe also bridge that with a physical Ethernet device?
Yes, of course, of course.
And then maybe provide an entire LAN with onioncat?
Yes, that also would work, but if you bridge it to a complete network with physical machines, you maybe have to set up routing. It depends on how you configure your network, but basically it works, yes. Don't be shy. We speak German, so you can also ask in German.
OpenVPN is supposed to be working in about half a year with Tor when they implement UDP support. I think it's in their 3-year roadmap, and it's supposed to be half a year away.
Do you mean that OpenVPN supports some kind of Tor transport? Is it?
No, it's supposed to work well, kind of right out of the box when Tor has the UDP and TCP support. Currently, it only has TCP support.
Okay, you mean if Tor supports UDP, then it would be possible to transport OpenVPN through Tor?
Exactly.
Yes, of course, that's possible to do this. But OpenVPN is really a VPN. And if you transport the OpenVPN packets through Tor, they exit somewhere. The big benefit of onioncat is that we use hidden services, so the traffic never exits. And the second thing is that we have this kind of dynamic setup. We translate the hidden service URL to an IPv6 address, so nobody has to do some setup. They are automatically connected together in a closed user group.
Is the software good enough to be distributed for Linux distribution or something like that for the moment.
You mean if we build some packages for distributions?
Yeah.
Well, the short answer is no. A little bit longer answer, I talked to some guys here on the Congress, and I hope that we will get some packages for Debian and other distributions, but that's a real hard work. That's the most work. Coding this stuff is nothing compared to getting packages right and writing autoconf and automake and all that stuff. So we do not have any packages currently. But download it, configure, make, install. It's really, it should work. There are no much dependencies currently, so it should be easy for everybody who is familiar with compiling software to use it. Okay.
Does a hidden service have to run on a Tor node actually, or is a Tor connection from my hidden service server sufficient? And the other question is, when can I reach Pirate Bay via this service?
Sorry, I didn't understand the second question. But the first question, basically you do not need hidden services on both ends. You just need it on one end, of course. But if you don't have a hidden service configured, we cannot do this translation stuff because there is no onion URL. So you would have to configure the IP address on the one end, on the client end yourself. But it would work, yes.
And for the second question, just ask the guys at the Pirate Bay to host the services into onioncat. It's that simple.
Well, I just have a proposal for the top-level domain. Just call it dog.
We also thought about calling it snail because it's slow.
Onion snail.
Is it also working through NAT?
Is it working through NAT? Well,
With the IPv4 extension, it should work with NAT. So if you
well,
implement...
yes, it should work, of course. So you don't have to have Tor and onioncat on the same host. Tor can be somewhere else. You just have to make sure that the onioncat can reach the SOX port on the SOX interface of the Tor proxy. So if there is NAT in between, it doesn't matter because, well, yeah, it's transparent this way. It's a TCP session.
With some statical NAT entries and with the IPv4, it should be easily possible.
No, dynamically, it would work through.
Okay.
No more questions, then I'd like to thank both of the speakers for their informative talk and a small applause.